Okay, welcome people of the NCGNT seminar. Today's speaker is John Boiquaye from the University of Ghana, and he's going to talk about twisted nerve of a group and the Böhm Ștefan construction. Please.
Okay, please, can you see my slides?
Yes, you can see them.
Okay, right, okay. Yes, so I would first want to give a brief introduction, then a motivation as to why we are doing this and what we really want to look at. And then I'll talk about the categories of interest and then discuss distributive laws, and then talk about differential objects, and then differential objects from commoners, and then some results as examples. So differential objects are some sort of variation of the well-known differential objects which we have in homotopy theory and homological algebra. And this is actually a generalization of the concept of cyclic objects due to Alain Connes. Now, cyclic objects are central in defining cyclic homology, which is one of the building blocks of Connes non-commutative geometry. Now, for various variations of cyclic homology, like the Hopf cyclic homology and equivariant cyclic homology, one must go beyond cyclic objects, and that is when we do make use of differential objects. Now, Böhm and Ștefan gave a general construction method of cyclic objects using distributive laws, and what they actually do is that they more like consider the extra data that one needs to turn a simplicial object formed from a comonad into a differential one. And we understand that, okay, if you have a comonad, you can form a simplicial object from that. Now, if you get a second comonad and a distributive law between these two ones, then you would be able to define, or let's say put some sort of simplicial structure on this simplicial object. Okay, so why are we doing this? We want to answer the question, when does a simplicial object in a category that computes the simplicial homology of an algebraic structure carry a differential structure? And the main example is the canonical simplicial F module whose n simplices are the elements of M tensor U tensor with itself n times tensor n, and its homology is tau with M and N being coefficients, and we have U as an associative unital F algebra. Now, this has been done for various cases where U is a Hopf algebra or a Hopf algebroid. Now, Kowalski, Kramer, and Slevin studied the above question for the example from the results of Böhm and Ștefan, and this leads to a complete description of additional structures on M and N that turn these simplicial objects CU and MN into a differential one. However, they were only able to give a description for N, but it was vague. They couldn't give an explicit description for the coefficient M, and in this paper which we have on the archive, which actually a joint work with Ulrich Kramer and Bartulovic, we were able to give a complete description of the additional structures on M. All right, so what do we want to do here? We want to look at the top algebra in the categories set of sets, which is a group G. And then if we want to look at modules over a Huffle algebra, in the category of set, we would want to be looking at something like G sets and so some things like G sets. So from this information, we would actually obtain a simplicial set with simplices given by this Cartesian product. And when M and N are just the trivial one-point sets, we have what we call the nerve of the group G. Now, in Weibel, the nerve of a group G can always be turned into a cyclic set. I think I would demonstrate that. And in Loday's cyclic homology, we see how this cyclic set from the nerve of the group is a special case of what he called the twisted nerve of a group. Now, in both examples, we have that the coefficients M and N are trivial G sets. So we can now start with something. So first, we know what the category of sets are. So the object there are sets, and we have the morphisms as set maps. And then we have the category of G sets, where the objects are G sets and the morphisms are G equivalent maps. By G equivalent maps, we mean that the function, let's say the morphism between any two G sets is compatible with the action of the group. Okay, so I think whilst Julius was speaking, he spoke about how to write down a bar construction and a co-bar construction. And usually these things do stem from what we call an adjunction. I mean, of course, one can just write a bar construction for that by making use of the let's say for a co-monad, you make use of the co-multiplication and the co-unit. For a monad, you make use of the multiplication and the unit. Yes, so in our case, we would want to get a co-monad from an adjunction, and from that, we would use to construct a simplicial object. So adjunctions. So if we let C and D be two categories, then adjunction from C to D is a triple where we have F as a functor. In this case, F would be the left adjoint, U is the right adjoint. And we have a bijection between the form sets, which is natural in C and D. Yes, so I think I'll just skip this since Julius has spoken about comonads. Now, I would give an example of a comonad, and maybe just make some few clarifications to what Julius said. So if I take, okay, so I try to write, I don't know. Okay, right. Please, can you see this? I try to write on these slides. Please, can you see it?
Yes, we can see you writing.
Okay, all right. So if I take L to be a G set, and I take, so I fix this L. Now, if I take any G set N, then I can form this Cartesian product. Now, this guy is again a G set Y because then I can act diagonally on this. So the action on this becomes GL, GN. So this can actually be extended to an endofunctor on the category of G sets because it takes G sets and it produces G sets. So this qualifies to be an endofunctor on the category of G sets. We would write this as this, and we need natural transformations to accompany this so that we can call this a comonad. Now the coproduct is given by this. So again, we duplicate the L, and then we just maintain the N, and then with the co-unit, we do nothing to the we do nothing to the N. We only split out the N, and this gives us a comonad on the category of G sets. Now the other comonad which we would use, this stems from the adjunction between sets and G sets. So here, what we actually have is we have sets here. We have G sets up there, and this is a free functor. This is a forgetful functor from the from G set to set. So this U actually forgets the action of the group on the set X. And so we first come down. Let's say we move from G sets with U, and then we move back again to G sets. So when we compose these two, we get an endofunctor from G sets to G sets. So this is an endofunctor, and what does it do? I mean, but usually we'll just write this guy as dash because U takes in a G set, forgets the action, and it gives us back only the set. So this will take in, let's say, some G set, say N, and it's going to give us G cross tilde N. Now, I use the G cross tilde N to differentiate between this one and the one which I have up there, because in case the L there is a G, then if I don't differentiate between them, there'll be some sort of confusion. So here we have this guy, and now the natural transformation delta lower n goes to G cross tilde N. And now what this does is that it just puts one yes, the one after G. I think this should correct what Julius said. So the one is not in front of the G, it is after the G. It is one there, and then the epsilon will just act. So they just the action of G on it. So this comonad T comes from the adjunction between this between sets and G sets.
If I may, let me ask you if I got it. So you write the tilde over the cross to say that you just act on the first vector, while if you don't write the tilde, this means that you act on both. Is this correct? Or?
Yes. So the one with the tilde means that this very comonad is coming from an adjunction, or let's say it's coming from an Eilenberg-Moore adjunction. I think I have to clarify because from every monad or from every comonad, one can get an adjunction, but this one is coming from an Eilenberg-Moore adjunction. So yes, so here the Here, the one with the tilde means that we would act, and with the coproduct, we have one after the gene. Meanwhile, here we just have a diagonal action.
Okay, thank you.
Okay. Distributive law. So given two monads or two comonads, if we want to compose them to get another monad or another comonad, what we need to use is called a distributive law. So it helps us to compose two monads or comonads to get another one. All right. So so this is a natural transformation going from this from these two endofunctors. So S and T are both endofunctors on the same category. So we have S, let's say taking the category C to C and T doing same. And these ball diagrams must commute in order for us to call chi. In order for us to call chi a distributive law. We can define it between monads, between comonads. We can also do this between monads and comonads. In that case, it's called a mixed distributive law. Okay, so here we have so first with this very diagram, what we do is that we keep the T fixed and we just operate on the S. So here we keep the T fixed, we apply the coproduct to the S to get TSS. Then we apply chi between these two guys in order to get this one, whilst we keep this S fixed. Then we apply chi again between these two. And then we can now go back in the other direction, where first we apply the distributive law, and then we apply delta S. Here we would keep the S fixed whilst we work with the T. So here we apply the coproduct on T, and then here we apply the distributive law, and then we do that again. Then we can go back the other way, and this diagram must commute. Now with this, what we do is we first apply the apply chi, and then we apply the co-unit on the S. So here to just keep the T fixed whilst we only work on the S. Meanwhile, here would keep the S fixed and then just work with the T. First apply chi from here, and apply the co-unit on T, and then we do the co-unit on T here as well. So yes, that should that is that for this one. Okay. All right. So okay, sorry about. I think this should have been on the previous slide. So yes, I'll give you an example of a distributive law. So let S and T be the examples of comonads on the gene. So here we have our T as this gene cross tilde blank, and then here we have our S as the L cross blank. Okay. And what we are saying here is that this very natural transformation, which takes some k from G, L from L, and N from N, and gives us k of k, comma n, is a unique distributive law between the comonads T and S. The next one is what we call a right-chi co-algebra. So these actually these are more like co-algebra structures on the distributive law. It's this. Well, okay, all right. I think I'll say something about that later on. All right. So a right-chi co-algebra is a triple where we have rho to be a natural transformation from Tn to Sn. We have n to be a functor. Now this is any category. So And then we have C to be the category we are interested in. And we need these diagrams to commute. So again, here I apply the product on T, and then I apply rho, apply chi, and then I apply rho again. And this should be the same thing as me first applying rho here, then applying delta on S. Then with this one, I apply rho, that takes it from T into Sn, then I apply epsilon on S, and this should be the same thing as me applying epsilon on T. So an example of a right typo algebra is this. So take N to be a G set. F is any set map. Then a natural transformation, rho n from G cross theta n to L cross n, which takes any pair AN to AFN, AF of n, comma AN. This is a right typo algebra. So in other words, this very map must satisfy these two diagrams. Then we have what we call a left typo algebra. Again, this is a
John, could you go? Sorry, John. Could you go one slide up? Yes, to this slide here. So in the chi here that you have in this example is the same chi that you had in the previous one, that is just flipping and kind of you duplicate and then act on the first one or something?
Yes, here, yes.
Yeah, okay.
Yes.
So this is like an extension of this example here.
Okay, so yes. So I give an example of a chi, and I give examples of what a right typo algebra is and what a left typo algebra is. Yes, using the same chi. Yes.
Thank you.
Okay. So for a left typo algebra, this is a triple where we have M to be a functor from the category in question to this is any category. So for those who are interested, in doing some sort of homology, one can send this to the category of abelian groups. I think one can do that, and then one can study homology there. So let's like algebra, which is a triple. We have M to be a functor from C to any category. We have lambda to be a natural transformation. And we have that the following diagrams must commute. So here we have the M on the left side of the functors, and here we have S going to SS. We apply the co-product, and then we apply lambda here on this guy, and then here we apply chi on these two guys, and then we apply lambda again. So this just drew out to the case of the right chi co-algebra. So here we apply the lambda S again. We apply the lambda here, and then we go back. We can first apply lambda, then we apply the co-product on the T. And we first apply lambda, and we apply the epsilon on T. The same thing as we applying the epsilon on the S. And I give you an example of a left chi algebra using the same chi that we've seen before. So if I take M tilde to be a functor from G set to set, and what this does is that it takes any G set X to the set of orbits in X. Sorry about that. Okay, so we first need H, which is a G equivariant map from L to G, and we define lambda tilde n to be a map going from L cross n to G cross tilde n. We claim that this very map is G equivariant, and then we conclude that the natural transformation, which first what it does is takes L cross n, then applies the functor m tilde. Again, we have this guy which also applies m tilde on this guy. So this lambda, we claim this is a left Kaiko algebra. In other words, this must satisfy these two diagrams there. Okay. Yes. So Julius spoke about simplicial objects, and for that matter, I think I would skip, but I think I'll just say something little here. Yes. So here, I think we just have the. Alternatively, we can write what he spoke about a simplicial object in a category, say C, this way, where you have this. I think so. These are the simplicial relations that he was referring to. That if I have I to be less than j, then if I do if I do d lower I, d lower j, this should be the same thing as me doing dj minus 1 di. And if I do si xj, this should be the same thing as me doing sj plus 1 si for I less than or equal to j. For I less than or equal to j. And then the compatibilities between the phase maps and the degeneracies, we have that if I do di xj for I less than j, then sj minus 1, then sj minus 1 di must be the same thing as the di xj. And if I have that I is equal to j or I is equal to j plus 1, then di xj must be the identity. And if I have I to be greater than or equal to j plus 1, greater than j plus 1, then di xj must be equal to xj di minus 1. So I think he said all about that. Now we want to go a step further. We now want to more like add more structure to a simplicial object, and we want an additional map Tn that goes from xn to xn, and this map must satisfy these two conditions, or these two relations. That if I have di t, this should be the same as me doing t di minus 1 for I line between 1 and n, which 1 and n inclusive, and then dit should be equal to dn for I equals to 0. And then sjt should be the same as t sj minus 1 for j line between 1 and n with 1 and n inclusive, and sjt must be the same as t squared sn for j equals to 0. Now, if it happened that after composing t with itself n plus 1 times, I get the identity, then I say that this differential object is cyclic. Else, if I don't get this, then it is only a differential object. Okay. So now, want to
maybe I can ask a question about this definition. So if I recall, Julius gave a slightly different definition of a simplicial object, right? So he said that a simplicial object in a category is a functor from the opposite of the simplicial category to the category, right? And then the theorem said kind of that this is the same thing as asking that you have the xn's and the di's and so on. So my question is, what would be the functor version of this definition here?
Okay, so here what we actually have is we have a contravariant functor. What should I use? Okay, I could use K for duplicial. So I have K here. What's K dash is that? So this would go from what we call the duplicial category. How do I denote this? What notation should I use? Okay, I'll use D. So this would go from, so either I take the guy to be a contravariant functor from the duplicial category to, in this case, to any category C, or I take this to be the covariant functor from the opposite of this very category to that. Now, the simplicial relations that he mentioned will all hold. So we'll then have so I'm using this one because after applying this very functor, I would then be using these guys as these straight DIs. So these ones would then go from let's say I'll use this N to M. Then we would also have this S. Okay, maybe I think I would just give me. Let me just go this one. Let me first state this before I do this. So I have these things here. The objects here are things of this form. So these are ordinals here. The maps are just the same thing as the one that he spoke about, but with extra information. So the extra, so this N to M, with the extra information being that if I do Fj plus N plus 1, the same thing as me doing Fj plus M plus 1. F of 0 should be greater than or equal to 0. And here this F is actually going from Z to Z. Again, these are non-decreasing maps. And then I think lastly, I have that F of N is less than or equal to M. Yes, I think
I see. So basically the functor definition would be the same. You just change the category on the left side.
Yes, yes. Okay. And we have more information there.
Okay.
Yes.
Thank you.
Right. Welcome. All right. So as an example, so we want to look at this simplicial set. So whenever I think all right. So given let's say a category, a group is a category with one object. You can look at what we call the naive of a category, or let's say the naive of a group. You are looking at the all composable maps going from G to G. So if I use this guy to denote the object in, in G as a group with G, a group as a category with one object. I'm looking at all the composable maps. So I'm just doing this, all the composable maps, and because in that case the elements in the group are the morphisms, I just have G2, G3. I mean all the all possible combinations, and so forth and so on. So I collect all of these composable maps on G, and that gives me a set which I call the naive of a group. Now this is a simplicial set. Why? Because I can have my DI as reducing. For example, if let's say if I have Cn, I'll go down to Cn minus 1. What I have to do is, if, for example, this is my 0 term, my 1 term, my second term, third term, and I want to apply, let's say, for example, D2, what I have to do is that I multiply. So this is 0, 1, 2. So I multiply these two guys, thereby reducing the length of the morphisms, and so that goes down to let's say if this were to be C5, that will go down to C4. So the phase maps are actually given by multiplication of elements in the group. The degeneracies are given by you inserting the identity element between the point in question. So this is actually a simplicial set. One can verify that all these simplicial relations hold. Okay. Then I can turn this simplicial set into a duplicial and a cyclic set by applying this operator T. And this is well known. One will find this in Weibel's book on molecular algebra, and also in Loday's book as well. So what is that it takes any it takes this in G plus n, and what it does is that it will multiply to first give me this one G1, multiply G1 up to Gn, and then take the inverse of that. Then we have the G1 term all the way to Gn minus 1 term. Now this is a cyclic set, and this is the only cyclic set for the nerve of a group. Now, how do I form duplicial objects from co-monads? As I mentioned earlier on, I first I would need an adjunction, and then from that I would get a comonad, and I'll make use of the comonad structure maps to define the to put a simplicial object structure on whatever I want to define. So here, if you see this delta would actually expand. If I want to go from let's say Cn to Cn plus 1, wherever I want to put that in there, I would have to use the delta, and if I want to contract it, go down, I would have to make use of the epsilon. So that would just contract it. So yes, I would now want to speak about the bar construction. So if I take n to be a functor from any category at all, pi to beta, the bar resolution of n is a simplicial functor btn, which goes from pi to b, defined by this. So we have this simplicial. Sorry, we have this object here where you actually do n plus 1 times of this t, and then we have the di's given by you using this one to kill them. That is, so if you want to constrict, you apply the epsilon to kill. If you want to expand the terms, that is, go from a lower degree to a higher degree, you then apply the sj's, and you apply the delta in the required position. And as you know, our di's and our edges are the phase and the degeneracy maps respectively. Now, if I take an additional functor m from B to Z, and then I apply that to the simplicial functor, this btn, I get a new simplicial functor, which we call CTMN. Now, Böhm and Ștefan construction tells us it tells us that if we have S to be a comonad on C, we have chi to be a comonad distributive law. If we have N and M to be right and left chi co-algebras, respectively. And if we denote lambda to the power n by applying the natural, applying chi n times, that is doing this, okay, applying chi n times. And if we have tau n to be a natural transformation going from this simplicial functor to this, to this very simplicial functor, then Tn, which is the differential object or a cyclic object, can be obtained by composing, first doing this one, composing that one with this, and composing that one with that. So in essence, what this is saying is, if you recall this simplicial, this cyclic object that we define here, if indeed this would arise by the Bohm-Ștefan construction, then if we get two comonads, chi between them, we get a right chi coalgebra and a left chi coalgebra. We can compose them to get this T. So in essence, that is the story behind the Bohm-Ștefan construction. Okay, so I give you an example of a bar construction. So here I take n, the functor. Here, if you recall, this was supposed to be any category. So I just choose, I just use the terminal category in order to obtain n as an object in the category of G sets. And I define my m tilde to be a functor going from set G to set by doing this. Okay, so I first do m cross x, and then I pick the orbit of that. M is any G set. Then the bar resolution, which goes from this terminal category to set, is given by this. This is a simplicial set where I have my SIs defined this way, and my phase maps also defined in this way. So with the SIs are in set 1 between the GI and the GI plus 1 term, with the I's, if I is equal to 0, I multiply on the left by G, that is, I act on the left by G1 inverse. For I between 1 and n minus 1, I multiply the I plus 1 term and the G I plus 2 term. And if I is equal to n, I act on the y. How much time do I have left? Yes, how much time? Okay, all right. So working with orbits is not pleasant. So we use an identification whereby I change this into I transform this into that. This is a bijection with the inverse map given by this. And now under this identification, I have this simplicial set. So with the SIs, I have 1 inserted between the GI and the GI plus 1 term. With the phase maps, I have for I 0, I equals 0, I have again action of G 1 inverse on X. For I between for I from 1 to n minus 1, I multiply the I term with the I plus 1 term, and for I equal to n, I act on the y. So as you can see, this gives me a generalization of the classifying space of a group, or let's say of the nerve of a group. With the nerve, we have the M and the N's as being the 1-point set. So when M is this, you have N to be that. This would give me the nerve of a group. So the next thing is that we classify all the differential structures on this simplicial set. And so we consider this simplicial set that we have. Now, if you notice, I have turned my M to be, I have taken the M to be a terminal G set. Now, that was to make life easy for me, because having the M here, this became a bit difficult, but actually there is an isomorphism from this, going from this one to we have in G n plus 1 cross the think we take n cross m. So I think this sounds sort of adjoint, yeah. So there is an isomorphism that link this that's link this to. So that gives me a way to go about this very problem dealing with this guy. So without loss of generality, I can take this M to be the terminal G set, and I have my N. I can define this. I define my T in this form. I define T in this form, and then actually I define T as taking G1 up to GNY to this. Now here, this alpha is a map going from N to G. This is any set map. And we claim that this is a classification of all the differential structures formed from the nerve of a group. Okay. Yes, yeah, so a sketch of the proof is that we need to verify that the differential relations hold. We then assume that given T as this, we must given T as this with F lower Y going from that to N, and Fi going from this one to G, we must check that all the differential relations are satisfied. Now, in doing so, we would end up with some conditions, and that is what actually leads us to writing this one as what it is. I would like to demonstrate if there is some extra time, but yes. So I think as a corollary, what we have up here is not cyclic. It's only a differential object, because when we do this t to the power n plus 1 times, we don't get the identity. However, if we claim, if we set alpha y to be in the center of the group, then this becomes cyclic. But yes, okay. Sorry about that. Yes, so we, as an example, we let we let this CG trivial set N be the simple set that we have discussed above. We take Z to be an element in the center of the group. Then for any element Y in N, we have T defined by this as a cyclic operator. And this is what Lode termed as the twisted nerve of a group. And what we have done is that with in Lode again, this n is the 1-point set. So what we've done is to generalize Lode's twisted net of a group by just considering any general G set n. As a remark, if I have alpha to be n from G as um, satisfying an additional property that's alpha GY gives me G alpha of Y G inverse. So this is actually a cross G set. Think about cross models. Then in that case, we do not require that N be a trivial G set for T to be a cyclic operator, because up there we needed the condition that although N is general, the group must act on it trivially. But in the event that we don't want the N, I mean, if we don't want the N to be trivial, but N to be any general G set, then we will need that N must, I mean, there must be this additional structure that alpha must satisfy. That is, N must be across G set. And we would need that alpha Y should be in the stabilizer of Y for any Y N. Okay, 7 minutes more. Okay, so recall the chi, the rho, and the lambda, which we have defined above. If we have that L is a faithful G set, and if we consider the T to be the differential operator, which we have defined above, that is this T, that is this T. If we define alpha of Y to be the inverse of h of f of y, then I can write a T that we defined as a composition of this, as that of rho, chi, and lambda, meaning that the differential operator or the cyclic operator which we got arises from the Bohm-Ștefan construction. So just as a as a sketch of the proof, one has to compute this, use the identification that I mentioned, and then one must show that T is indeed equal to these composites. So this, in the nutshell, means that the differential operator T always arises from the Bohm-Ștefan construction. Thank you. These are some references.
Thank you, John. All right. Are there some questions or comments?
A very, I don't know, naive question. So from my understanding of the simplicial complex, one of the reasons it was introduced was by cyclic cohomology, as you mentioned at the start, as a motivation. So is there some connection back to cyclic cohomology for the duplicial case?
Okay, so with the duplicial case, it is not always that you get the operator T being cyclic. I think if you want it to be cyclic, you have to put some sort of restriction on the category in question. So if you look at half algebras and you form, let's say, you do the bar construction with that, you get a simplicial object from that. You take your I think you then have to put let's say the operator T on that. you can, I think, by using Oxshield, I think the Oxshield complex also, of course, you'll be able to do homology with that. But if you want it to be cyclic, then the modules in question, which is actually the Yetta Greenfield modules, have to be restricted to what we call the stable anti. I think that the stable Yetta Greenfield uh, modules. I think in that case, uh, because we are dealing with the Hopf algebra, I think both the let's say the anti and the, I mean, I think they are both the same. So we just have to restrict from the stable anti-Yetta, sorry, from the Yetta derivative models to the stable anti-Yetta Greenfield models in order to get cyclic start. But to answer your question, we can still work with the duplicial ones, something like the half cyclic. I mean, the twisted cyclic homology and the half cyclic. Yes, we can just use the duplicial object for that.
Okay, thank you.
And maybe I can also ask a question, since you mentioned Hopf algebras. I mean, some people in the group here like Hopf stuff. So if we look at some of the examples that you gave, when we see like when you double a group element and then you look at the inverse, like some people here might think, okay, this is the coproduct and this is the antipode. So the question would be, can you do something similar using Hopf algebras rather than groups?
Yes, so I think from the start of the talk, I'm just looking at Hopf algebras in the category of sets. So the actually what your observations are all correct. All I'm just doing is just doing Hopf algebra in the category of sets. So the inverses which you saw, yes, I'm applying the antipodes. And then applying the co-product. I mean the co-algebra, which spits out the gene cross G and stuff. Yes, I'm just doing Hopf algebra, but in the category of sets. So yeah. So in case we want to do that, we just have to linearize. So with the sets, you linearize that to get vector spaces, and then you look at the group G as a Hopf algebra. The models over that become models over the Hopf algebra, and then you can talk about your coefficients, right and the right and the left ones. So yes.
So you say that everything here also works if you look at Hopf algebras in the category of vector spaces?
Yes, we only have to generalize.
Okay, very good.
Sorry,
so and then
linearize.
what about Hopf algebras in braided monoidal categories?
Okay, now that is another one. I think with the braided monoidal categories, that is what I'm thinking about next. That is actually with crowd G sets.
Okay, so this is future work, but could possibly also work.
Yes, actually, it works. It works. I'm almost done doing some things on that. Yes.
Okay, nice, wonderful. Are there more questions? Maybe even from online people, if there are any. If not, let's thank John for the nice talk. Thank you.
Nice to present here. I'm very grateful.